Hello, my name is Nicholas Candello. This is my Physics 2212 Lab 3 video report. An introduction to this lab. The purpose of this lab is to find correlations between magnetic field components at various distances and angles from a bar magnet. Additionally, we're going to try to formulate a general equation for all of these different cases. And we're going to represent magnetic fields using a computational model. The results of this experiment showed that a bar magnet's behavior is similar to an electric dipole, which we studied earlier in the semester, and that the calculated exponent of proportionality for a bar magnet was negative 5.71. Some concepts you have to know for this lab are the Biot-Savart law, which tells you the magnitude and direction of an electric or a magnetic field based on the radius from the magnetic source. Additionally, you'll need to know the distance dependence of a bar magnet, which is shown, and how you can manipulate that equation to have a linear correlation between the electric field, or the magnetic field and the radius. So in this experiment, we used the magnetometer in our phone to calculate the magnetic field at certain distances from a bar magnet. Now we oriented our phone and the magnet in such a way that it is orthogonal to the Earth's magnetic field. That way it does not affect our measurements. Then we computed distances for various magnetic field values and recorded those in our spreadsheet, which we'll see later. Then we computed the magnetic field at a 45-degree angle shown on the right, and this shows how there is a different equation for when it's not directly on the axis. So the experimental calculations, on the left you can see the various the various data points for different fixed magnetic field values, and on the right you can see the graph of the natural log of the magnetic field and the natural log of the radius, which forms a linear correlation where the slope is negative 5.71. Continuing on, we observed at an off-axis field, so at 45 degrees, and you'll see that the average perpendicular distance was 14.66 centimeters, and the direct distance at the angle was 0.207 meters. And on the right, you can see the calculations for calculating mu using the formula given and the Biot-Savart law. We can calculate that mu is 0.005. Going on to the computational model, in the top left, you can see a function that calculates the magnetic field given a magnetic moment value and an observation location. In the bottom left, you can see the definition of 6 vectors, 2 of which are on axis and the other 4 of which are perpendicular to the magnetic bar moment. On the right, you can see the calculations for the axes, or the magnitudes of these 6 vectors. If you'll notice, the ones that are perpendicular have twice the magnitude as, the ones on axis have twice the magnitude as the other 4 that are perpendicular, similar to a dipole. On the left, you can see the calculations for the tiny purple arrow in the top left, which is at 45-degree angle, and there is the function describing, the lines of code describing how we came up with the direction and magnitude of that arrow. So some additional questions. Which of the following were observed during this experiment? When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. It was observed when the magnetometer was super far away from the magnet. There was almost no sources of magnetic fields in the x direction, so it was close to 0. We did not observe that the magnetometer moves close. That when it moves closer to the magnet, the x component decreases. It's the opposite; it should increase. The position of the magnetometer has no effect on the measured x component. This is not true. We saw as we move farther away that the x component decreased, and as we move closer, it increased. And then as the magnetometer moves closer to the magnet, the x component increases because the magnetic field strength is greater. And finally, what if you hadn't oriented your experiment to compensate for the magnetic north? How would your results have changed? If we oriented it exactly not east to west, so that it wasn't affected by Earth's magnetic field, then our calculations would be slightly off, and we'd have to account in some way for the disturbances in the Earth's magnetic field in our calculations. What if you were to stick 2 identical magnets together and run it again? The direction of all of our magnetic fields would stay the same, but our magnitudes will be greater because we have a bigger magnetic source. There's more magnetic material, so it would kind of like double everything. And thank you for watching.